Hello, we are the Stony Brook Robot Design Team based in Long Island in New York. This is our first year competing in the University Rover Challenge and our very first rover, Triton.
The mechanical team's goal this year was to have a durable and dependable rover capable of traversing rough terrain, performing specialized tasks, and collecting soil samples. The team is broken up into three major subsystems: chassis, suspension, and arm. The chassis of the Triton was designed in SolidWorks, and the main frame is made with square aluminum tubes due to its ability to be machined, assembled, and modified easily. The shape of the frame minimizes the use of tubes to decrease weight and to only provide supports wherever needed. A notable component of the chassis is the camera stand, which can be raised to provide optimum viewing angles or lowered to keep a low center of gravity while climbing up steep hills. The rocker bogie suspension design enables the rocker to go over large obstacles, which are more than half the wheel's height. On the suspension, the legs were optimized for weight, strength, and shape using finite element analysis and then CNC'd from aluminum. Triton's arm has 6 degrees of freedom, providing it with the dexterity to tackle the extreme retrieval and delivery task and equipment servicing task. We chose to use linear actuators instead of the motors on the arm because the actuators can be placed at higher position on the arm, which uses less power to lift. The rover's custom designed hand uses high torque servo motors to allow greater resolution of movement. The hand also has a worm gear to lock onto objects and maintain its grip without powering the servo.
This year's electrical system was designed completely in-house because of our requirement for Triton to be both reliable and robust, which we were able to achieve with our unique long-range beacon mode and 518 watt-hour lithium polymer battery solution. The power board introduces 3 individual step-down voltage regulators for all of Triton's peripherals. Thermal design was a major concern for us this year, which is why our power board is 4 layers and our electrical box design provides ventilation for convection airflow cooling. Triton's drivetrain uses 6 brushed DC motors with Hall effect encoders and 3 dedicated dual output H bridges. The brush motors accommodate simple movement scheme, and the encoders serve as feedback for Triton's PID control loop algorithms. The onboard PCB is both versatile and modular, as it incorporates control for the linear actuators, servo motors, and bipolar stepper motors we have on the rover. Triton's sensor board design integrates a GPS, inertial measurement unit, and various other data acquisition peripherals. We achieved this using a single Atmel-based microcontroller capable of handling high-speed serial communication and high-fidelity analog measurements. Finally, Triton's communications system integrates an extremely unique and robust low-power, long-range beacon mode. This is crucial to ensure the rover can be communicated with in areas with no line of sight.
We developed our software design with a focus on simplicity and efficiency. Using the ROS framework, our overall system is divided into several independent subsystems that work and communicate with each other. The system is able to quickly detect communication loss and corrupted data so that the rover can continue to function in any circumstance. We also use 2 radios for additional bandwidth and redundant safety protocols. Triton's control system uses an Xbox controller for movement and a joystick for arm control. Our rover uses the ROS framework for most of the software subsystems. It allows various nodes to be tested and developed independently. We have also developed a user interface using RQT for data visualization. Our vision subsystem is implemented using a Z camera. The main vision processing is done on the rover with a Jetson TK1 SoC, using a modified orb slam algorithm to create a 3D point map and localize the rover. Triton primarily uses its vision and GPS systems for the autonomous traversal task. The rover navigates towards the target GPS waypoint and avoids obstacles that are identified using the orb slam map.
The science for Triton was developed through extensive research and consultations with professors who are currently working on the Mars 2020 rover. To accomplish the science cache task, we will focus on the detection of liquid water and deconstruct a sample's chemical profile to determine its potential to support microbial life. The drill and collection blocks provide a system for taking and storing soil samples without contamination. The camera attached to the sampling arm will take photos of the sampling site. Sensors on a rover will collect important in situ characterizations such as temperature, relative humidity, UV intensity, atmospheric pressure, and sample spectra. The spectra will be taken with a public lab's desktop spectrometer mounted on the rover. For the laboratory analysis, the sample's mineralogy will be observed through a petrographic microscope and contextualized using the in-situ data. Then it will be submerged in deionized water and its pH recorded. Further analysis will be conducted using the geochemist workbench by plotting dissolved species as a function of pH to determine its chemical composition.
At the Stony Brook Robot Design Team, our mission is to challenge aspiring engineers to build the future. We are excited to submit our system acceptance review for consideration towards URC 2018.